we are trying to look at the principle of Archimedes, and under these subheadings, in order to see this, as we are going to be using this as a guide in order to understand what we're about to discuss in terms of the principle of Archimedes. We are going to be looking at what is flotation. Then we'll proceed to factors upon which the weight of the fluid depends. Then we look at these factors include the density of fluid, the temperature of the fluid, and the mass of the fluid. Then we are also going to proceed to why does ice float on water. If you notice, if you have ice block and you place it on water, it's going to be floating on water. Then we have application of Archimedes principle, which are loss of weight by submerged objects. We also have flotation of bodies in liquid. Then we are going to look at it from the angle at which how ship floats on water. Then we proceed with question and answer session, and then the closing remarks. So we're going to begin. Archimedes principle. This is a principle that is very, very straightforward, and it is so important in our lives that it's the principle that guides the flotation of ships that are carrying heavy loads on the sea from one country to another. In fact, the small boats are also not left out. They also float on the surface of water based on the principle of Archimedes. So this will make us to look at what is flotation. Flotation is simply the act of an object not sinking to the bottom of an ocean or water. Now, in order for us to understand what we want to discuss very well, it will be very important for us to quickly dive into the factors upon which the weight of a fluid depends. There's this container in the left corner of my screen. I'm pointing at it with my pointer now. Can you see it?
I'm seeing fluid displaced.
No, on the body of the container itself.
Oh.
Can you see my pointer? I'm pointing just under the numbering on the container itself.
200 liters.
It's 2.00 liter. I don't know if any other person can see it.
2.00 liters. Yes.
Then what about the number under it on the scale? Because it is being placed on the scale.
19.6
Newton. That is 19.6 Newton. Now, what I'm trying to say now is that I am trying to tell you that if you have a specific quantity of fluid, for example, 2 liters, are you there? Now, the weight of that fluid is 19.6 what? 19.6 Newton. Now, I said something like factors. Are we there? Factors upon which the weight of fluid depends. So I just want to give you an instance. Factors upon which the weight of fluid depends. We have density of the fluid, temperature of the fluid, which means if you have a specific quantity of fluid of the same volume, are you getting what I'm saying now? They are not going to be weighing the same thing if they are of different substances, because the substances are of different density, because the density is a function of the weight of the fluid as well. Therefore, it's 2.0 liter, and we are seeing 19.6 Newton. Let me see if I can change the fluid. Okay, I think I can change the fluid density from here, and I can even change the fluid material. Now, if you look at this place, can you look at this place? Let's look at this place together. We will see something like water. Can you see it? I need this session to be interactive, please. Can you see water written here? The meaning is that water is what is inside this cylindrical container. So if I should change the water to something else, let's say to oil. Are you getting what I'm saying now? Okay, let me maintain water first. 2.0 liter, and then I will just change the density, the fluid density. Are we together? Now, by changing the fluid density, it means that something is happening. So, varying the density of the fluid, by varying the density of the fluid, temperature of the fluid, mass of the fluid, you can get different weights of liquid, even if they have the same substance. But if the density is not the same, the temperature is not the same, the weights will be changing. Now, the next thing is, why does ice float on water? Because the density of ice, are we together? The density of ice is less compared to that of water. So ice, as we are saying, ice is a solid, but it doesn't mean is denser than water. So what I'm telling you now is that ice is lighter in terms of density compared to water. Therefore, this is the reason why ice floats on water. Now, please, if you can see my screen, like I said, this is able to float in water because the density of the container is less than that of the water. Do you understand what I'm saying now? So the density of this container is less compared to that of the water, therefore is able to float in water. But mind you, all these ones, they are not something that we can control, because the density of a material depends on the nature of that material. Even though we can, it also depends on some things we can do about it. But naturally, if we're talking of natural elements, the density of the element depends on the nature of the elements. Now, can we look at this diagram? Let's first of all state what is Archimedes' principle. It says a body wholly or partially immersed in a fluid will be buoyed, meaning that it's going to pop up or to be acted upon upward by a force. Upward by a force that's been explained here. In a fluid will be buoyed upwards by a force equal to the weight of the fluid that is displaced. So this weight of the fluid that is displaced is now what is important to us. Now, can we all see this diagram? The meaning of this, the interpretation of this diagram is that if you put an object, look at this object from this side, you can see that this container is empty and we're able to fill this liquid to the brim. I mean, to the point whereby it can easily flow out when you keep something on it. So the meaning is that if you put anything inside this water now, the water will rush through this place because the water will tend to pop up. The water will be displaced by the volume of this particular substance, and then because there is a room for the liquid to displace, so the liquid are going to be dropping into this place. Now, if the liquid drops here, then we take it to a scale and measure it. So we discover that the amount of force that is acted upon by the fluid is acting force upward on the substance. Now, the amount of force is being quantified by the weight of the fluid that is displaced. I'm going to repeat myself. When you put the object inside the fluid, it's going to displace some quantity of fluid. Now, that quantity of fluid that is displaced quantify the amount of upward force, according to Archimedes' principle, that is being acted upon by this substance. In fact, if I don't know if all of us here have experienced fetching water from a well before. If you put a bucket inside a well, you will discover that when the bucket is completely submerged within the body of the fluid, if you are pulling it upward, the liquid will be acting upward on the container, such that you are not going to be feeling the weight of the container until it's completely out of the fluid. So the meaning is that there's a particular force that is acting in upward direction as any object is being submerged inside a fluid. The question is, what is the quantity of that force that is acting on any object that is inside the fluid? This is the way to get it. Archimedes proved to us that the amount of fluid that is displaced by the object when you completely submerge it within the fluid is, when you now weigh the quantity of water that is displaced here, that quantity of water exactly quantify the quantity of force that is acting in the upward direction against the motion, against the weight of this particular object. In 30 seconds, I'll still put it this way. The meaning is that, for example, if you weigh this liquid now and you discover that it's 3 Newton, the meaning is that 3 Newton force is acting in the upward direction against the weight of this substance. So what Archimedes tried to help us to do is the fact that it helps us to quantify the exact amount of force that is acting upward against the weight of an object that is being submerged in a fluid. Now, the next thing is, how do we then control the amount of force that is acting upward? Since we now know that it is a function of the quantity of fluid, then scientists now realize that we can change the shape of the object, still keeping the mass of the object and the weight to be the same. Because if you have a bottle of water now and you squash it into a very tiny size, it's going to be weighing exactly the same thing. Do you agree? The only thing that changes there is the volume. So if you put it inside this fluid, it will not have enough ability to displace the volume of fluid as much as it will be when you haven't squashed the container. So what we are saying is that it is now possible for us to control the amount of force that is acting upward against an object that is being submerged in a fluid. Now let's take a look at this. Now we now realize that if the weight of the object, let's take a look. Now, if the weight of an object is greater than the buoyant force simply means the force that is acting upward. You can see it labeled here as a result of the fluid applying a force on the object that is moving inside a fluid. If the weight of an object, these are now the condition now. This is condition for flotation. If the weight of an object is greater than the buoyant force, meaning that the weight of the object is greater than the upward force by the fluid, then the object will sink, because the downward force is going to knock down the less upward force. You can see from the size from the diagram. Now, the next thing is, let's take a look at this. If the weight of an object is less, that is to say, if the weight of an object is lower than the buoyant force, that is the force that is acting upward, it's also as if you are putting something on a table. The table produces a reaction that is greater, then the object will float. We now know the condition for an object to float now. So if the buoyant force is greater than the weight of an object, then the object is going to what? Is going to float. Then we can also have the object situating within the middle of the fluid as well. If the weight of an object and the buoyant force are exactly equal to each other, then the object will hover in the water. So we are not much concerned about this. We are concerned about this particular aspect of this of this diagram, which means the only thing we are looking for is that if this object sinks down, if this object sinks, what can we do in order to make the object not to sink? That means we have to be able to increase the buoyant force. And how do we increase the buoyant force? By simply changing the volume of this substance so that it can displace large volume of water, because the weight of the water or of the fluid depends on what? It depends on the volume of the fluid. So the higher the volume of the fluid, the higher the weight of the fluid. If you have a small quantity of fluid, you have a smaller weight. If you have a large volume of fluid, then you have a larger weight. So if there is a way we can manipulate the shape of the object so that it can displace a very large volume of fluid before it's completely submerged in the fluid, then it's going to be floating here. And this is exactly what Archimedes' principle is talking about. Now let's look at the ship. Can you see the ship now? Now, if you can see the ship now, this is a ship in the fluid. Now, this ship in the fluid has been designed in such a way that it has a very wide area, such that if you put it in a fluid, it will displace a very, very large volume of fluid before it's even completely submerged, or before it's even submerged to a reasonable length in the fluid. So you cannot compare when you squash the the ship. If you squash the ship together, you squash it together so that it becomes like a very small solid something, and you drop it in the water, you expect it to completely drop inside the water, isn't it? Because it will not have the ability to displace large volume of water. Let me see if I can use this one to talk of what I'm talking about. Now, can you see this now? Now, this is going to be displaying the amount of volume of water that is housed. Now, if you put it inside, let's see. Can you see it? As I'm putting it in the fluid, can you see that the volume? Hello, can you see it? Now, this is representing the amount of fluid that is displaced. So the meaning is that the weight of this, you can see that. Okay, let's weigh this guy to understand what I'm talking about. What's the weight of this thing? 19.6 Newton. Can we all see the weight at this place? This is 19.6 Newton. Now, if you put it inside the fluid now, this measures the buoyant force. Can you see it? Fluid displaced. This one is measuring the weight of the fluid displaced, and this one is measuring the weight of the object itself. You can see when you have not placed anything inside the fluid, you're having 0 Newton in the container. Can you understand it now? Now, if you now bring it into the fluid, take a look at what happened. What is the initial weight of the object? 19.6 Newton. Now, let's put it in the fluid. Now, the meaning of this is that the object floats as soon as the volume of fluid that is displaced weighs 19.6 Newton. As soon as the volume of the fluid displaced is now weighing 19.6 Newton, the meaning that the upward and the downward force are now counterbalancing each other. When they counterbalance each other, then equilibrium will set in. It means that the object is going to remain in position. You are being pulled by a particular amount of force. Another thing is also being pulled. The weight is acting downward. Then the buoyant force is acting upward. If the two forces are the same, then that object will be stationary. That is what is keeping the object in position. So now let's get back to the ship. So if you come back to the ship, the only thing that is happening is that we have designed the ship in such a way that once you place the ship on the surface of the liquid, are you getting what I'm saying? Let's look at it. This is 29.4 Newton. Are we there? So the only thing we do, okay, since we have weighed this one, and then the question is, what is the expected weight we added into this thing? Let's say this is the expected weight. This is what? That makes what? 49.0 Newton. So assuming that the total weight of the ship and the expected weight is 49.0 Newton. The question is, how do we design this ship such that it will produce enough buoyant force, enough upward force before the ship together with the object is completely submerged? So this is why the ship has been designed to have a very flat and very big surface in the outside. Now let's now put it back and see. Can you see that? Now let me put this. You will see, as soon as you add the weight, it will still be a little bit submerged. It will just adjust itself, adjust the volume of the fluid so that it can counterbalance the weight again. Oh wow. You see what happened? It drops the ship. So the meaning is that it cannot produce enough buoyant force. Do you understand what I'm saying now? It cannot produce enough buoyant force until it is completely sunk. Let me see it again. Okay, let me try to place it gently. Can you see it? So the meaning is that you cannot say because you know that it's going to contain it, you now raise it up like this and drop it. Can you see that? So you have to place everything gently inside it. Something like this. Are we clear?
Má ti já máa waste. Mo gbọ́dọ̀ make sure pé
Are we clear? Okay, let us try to show the buoyant force. Now, can you see that the buoyant force is what? 29.4 Newton. Why? Because when we measure the weight of the ship, it was what? It was 29.4 Newton. So as soon as you put it, the meaning is that the weight of the fluid that is displayed is also up to 29.4 Newton. So by the time you place this one inside it, let's take a look at what will happen to the fluid. Can you see the increase in the buoyant force? Can we see the increase in the buoyant force? Am I sure anybody is still with me? Let's change the size of the ship. Are we together? So this is in the absence of no problem. Program. Now the next thing is I'm expecting question and comments. Question and comments.
Like, I really enjoy it, and I think everything is better now, even the animation and distance. So it
All right,
was a
thank you very
good
much.
dramatical representation.
All right.
Thank you, sir.
Victor, Alpha, what about you?
Yes, I understand the concept.
Okay. That was a good one. That's exactly what we are doing here. We're going to be looking at all those principles, and so that we don't just be seeing things without understanding how they works. You see, ship will be carrying a very all this Zangote trailer is ships that are even carrying them. They would have loaded them first. They will now still put them inside the ship, and the ship will still float on the surface of the water and bring them from country to country. It's because we are able to precisely determine the buoyant force and why we are designing the ship together with the expected load that is to be carried by the ship. All right, thank you very much.